So next result is Gauss-Bonnet theorem. So statement of this result is for any curve which encloses a simply connected region R, the axis of the curve is equal to the total curvature of R, where axis of the curve is obtained by the equation of given below. Now, in this case, consider a curve, consider a surface, right? So that is a R, which is R vector function of u and v. So that is the equation of surface of class 3. So class 3 means it has continuous third order derivative. Suppose C is closed curve, as we know that what are closed and simply connected region. Suppose C is closed curve, boundary of simply connected region R. So R is the simply connected region and C is the boundary of closed curve boundary of some simply connected region. For example, if it is a some connected region, if it is a connected region, this outside the boundary is the closed curve boundary of simply connected region R. Right? Let CBA consist of n smooth arcs. That closed arc is divided into n smooth arcs that is started from A0, A1, A1, A2 and so on, En minus 1, En, and first and last point is connected. That's why it is a closed. And each arc be of class 2. And each arc be of class 2. Let alpha I be the angle between the tangent to the arcs AI minus 1 and AI and AI plus 1. That is the angle between these two arcs. So that we will better understand by geometry. So this can be shown in the geometry. So the closed boundary curve of a connected region R that is divided into arc that is A1, A2, arc this is A1, A2, right? A2, A3, A3, A4, and A4, A5, and so on. Here we taken An minus 1, An, right? But in this case, in order to geometrically representation, so we take up to A5. Now this is angle between, this is a first, this is A1, A5, A1, right? It's tangent, right? So this tangent, so angle between these two tangents, which is alpha 1. So angle between these two arc is alpha 1. And angle between these two arc is alpha 2. And angle between these two arc is alpha 3. Angle between these are alpha 4. And this is a alpha 5. As we discussed here, alpha I be the angle between the tangent to the arcs AI minus 1, AI and AI plus 1, right? So that is measured at AI such that these alpha I which lies between minus pi and pi. So this is a, if it lies between this, in this region. Now alpha n is the angle between the tangent to the arcs an minus 1 and an and a1, right? This is the, as we taken this alpha 1, this is a last curve and this is a first curve. So that is angle between these two curves, tangent between the two curves. If C is taken to be curvilinear polygon and alpha I are the exterior angle at the vertex AI, this is the exterior angles, right? Not these are interior angle. So these are exterior angles. So here we taken exterior angles. So then these are the exterior angles at the vertices of AI. The axis of curve is denoted and defined by. So remember this result. So this is a formula of axis of curve. This is axis of curve C, which is equal to 2 pi minus summation of alpha I. This is sum of exterior angle minus kappa g ds, that is integration around C, and kappa g geodesic curvature, right? So that is in equation number 1, where kappa g is the geodesic curvature of the arc which exists for each part of C except possibly at the vertices, right? Now from lovely formula to kappa g, we know that this kappa g, which is equal to theta dash, pu dash, and q v dash. So this is a q. Now q v dash. Now in differential order, this can be written as kappa g ds d theta, capital P du, and q dv. This is q dv. Where what is this is a p and this is a q, value of p and q. We have this d theta plus this summation of alpha I, which is equal to 2 pi, right? Why this is equal? Since curve v equal to constant form a family of region enclosed by C. That's why this total sum is equal to 2 pi. Since curve v equal to constant form a family in the region R enclosed by C, turns through 2 pi relative to these curve. So remember this result. So this values from this d theta around C, which is equal to 2 pi minus summation of I is running from 1 to n alpha I, that is equation number 3. Now substitute equation number 3 this in equation number 2 and then in equation number 1. So this is equation number 3. So first take this equation and substitute in this equation, right? So what we get this in place of this we get this values, that is 2 pi minus this summation of alpha I. So first take equation number 3 in equation number 2, right? Now take the value of equation number 2 in equation number 1. Okay? Then substitute these values in this equation, right? So this will be cancel out. So what we get on simple values, we get this P du plus Q dv. This is minus time integration around C. So by Green theorems, this line integral into converted into surface integral. This is curly Q by curly U minus curly P by curly V into du into dv. So this is a surface integration around region R. Now we know that the surface element ds, which is equal to capital H du into dv. So from this we can find the value of du and dv, that is a ds by h. So what we get? We get this is equal to here we substitute the value of du and dv. This is a ds by h, right? So this is can be written as exterior of C, which is equal to integration around R k into ds, where k is equal to minus 1 by h curly q by curly u minus curly p by curly p. So that is our result, that we want to find the value of ex of C. Now, in order to prove its uniqueness, in order to prove the uniqueness of a result, so this is our result. This is a Gauss-Bonnet theorem, right? Now uniqueness, if possible, then we have two values. One is k and second is k dash. So that satisfies equation number 4. If satisfy, then both are equal. If both are equal, then this, if they are equal, then difference is 0. If difference is 0, then suppose our purpose is to prove this value is equal to 0. So suppose these is not 0. This is not equal to k at some point. If these k and k dash are not equal, then out of these two, one must be greater. So suppose k dash is greater than k, it implies k dash minus k is greater than 0. Also we know that it is a continuous. If it is continuous, then integration is also greater than 0, which contradicts equation number 6. So it contradicts this equation because this integration is 0. Then our supposition is wrong. If our supposition is wrong, then k dash minus k equal to 0. If it is 0, then k is uniquely determined. The function k is called a, remember this is called a Gaussian curvature of the surface. That k is called Gaussian curvature of the surface, and it is an intrinsic invariant, right? The expression this is the, what is that? It is a total curvature of the region R. So remember, this is capital K is called Gaussian curvature, and this integration around R is called total curvature of the region. If R is total region, then its total curvature can be defined by this integration. And what is K? K is a Gaussian curvature, right? So that is our result. So I repeat once again. So in this case, in this Gauss-Bonnet theorem, our purpose is to prove the result, the excess of curve. Our purpose is to prove the excess of curve, that is by equation. And that equation is this equation. This is a this equation, excess of curve, that is written in this form, right? So this is excess of curve, that is a Gauss-Bonnet theorem, in which excess of curve we can find integration capital K into ds. What is capital K? It is a Gaussian curvature. And what is this integration? So that is a this integration excess of curve, that is the total curvature of this connected region, right? Now this is our Gauss-Bonnet theorem. This is very important result. Now we will apply this result to some application in the next lecture. So in the next lecture we will prove these two applications.